Hi everyone. In this video, I will walk you through how to compute monthly land surface temperature using Landsat 8 and 9 data in Google Earth Engine. We will go from raw satellite imagery all the way to clean, cloud-free monthly LST maps at 30-meter resolution, exported as GeoTIFF files ready for analysis. This workflow is especially useful if you are working on climate studies, vegetation analysis, or, as in my case, studying how temperature affects ecosystem productivity. So let's get started. For part one, which is user settings, let's start with the user-defined settings at the top. Here is basically define the time range from January 2024 to January 2025, and the spatial resolution, which is 30 meters, matching the Landsat images. The coordinate system explicitly defined as the EPSG 3857, which is stable for large exports, and the output folder in Google Drive. And most importantly, the tile size or shared pixels. Now, these shared pixels must be a multiple of 256. This is critical because Earth Engine splits the large exports into tiles, and this prevents export errors. We also define a visualization range from -10 to 50 degrees Celsius. And you can change this, which is suitable for your study area. And then comes the part two, area of interest. We define the area of interest for this code. Here, I assume the AOI is already drawn in the Earth Engine interface as a geometry. You can just click on the polygon sign and then draw the geometry on the map. And we convert it into a region and display it on the map. This ensures that all processing is spatially limited to our study area. Now move on to the part 3, which is Landsat data collection. We load the Landsat data, basically. I combined Landsat 8 and Landsat 9, both from collection 2, level 2, which already includes surface reflectance and thermal data. And we then filter by location, filter by date, and apply a cloud cover threshold of 10%. And you can change this threshold to your study area. For example, my study area is very large on the whole Mediterranean region, although I'm now showing only for Spain. So you can change this cloud threshold to much smaller, for example, 2% or 5% if your study area is very small. And for a larger area, 10% is basically nothing. And this step ensures that we are only working with relatively clean images. Now, part 4, the pre-processing function. This is one of the most important parts of the workflow. We define a function called prep, which prepares each image. Inside this function, we do 4 key things. The first one is cloud masking. We use the QA pixel band to remove clouds, cloud shadows, cirrus, snow, and invalid pixels. Basically, this ensures high quality data. And second is reflectance scaling. We convert raw digital numbers into surface reflectance using scale factors. And the third is NDVI calculation. We compute NDVI using near infrared, which is band 5 for Landsat images, and red, which is band 4 for Landsat images. This gives us vegetation information. For some reference, you can also use different methods. I use the NDVI based emissivity method for land surface temperature calculation. And the fourth one is brightness temperature. We extract thermal band 10 and convert it into brightness temperature in Kelvin. So after this function, each image now contains NDVI and brightness temperature. And then part 5, which is the core science, elastic calculation. This is where the actual land surface temperature is calculated. We define another function called add LST, in which step 1 is estimate emissivity. We use NDVI to estimate surface emissivity. Low NDVI refers to bare soil, high NDVI dense vegetation, and mixed NDVI calculated proportionality. This is crucial because emissivity affects thermal radiation. And step 2 is apply LST formula. We use a physics-based equation that corrects brightness temperature using emissivity. This step converts satellite thermal measurements into true land surface temperature. And step 3 is convert Kelvin to degrees Celsius. Finally, we subtract 273.15 to get the temperature in Celsius. So now each image has an LST band. And then comes part 6, where we move to temporal aggregation. We loop over each year, each month, and for every month, filter the images within that month, apply pre-processing and LST calculation, and take the median. And you can ask why median? Because it reduces noise, remaining clouds, and outliers. This gives us a robust monthly LST map. And finally, part 7, where we export the data. Each file is saved as a GeoTIFF, has 30-meter resolution, and is clipped to the area of interest. We also use tiling of file dimensions to avoid export limits and enable cloud-optimized GeoTIFF, which is efficient for GIS workflows. And each file is named like LST Mojai 2024-01, LST Mojai 2024-02, and so on. And finally, we create a preview for a selected month. We filter one month, compute LST, display it using a color palette from blue to red. This helps visually interpret temperature patterns. Blue is cooler areas and red is hotter areas. So overall, this script transforms raw Landsat data into scientifically meaningful temperature maps. And the key strengths of this workflow is that it uses physically based LST calculation, applies strong cloud masking, and produces consistent monthly datasets, scales to large regions. This kind of dataset is extremely useful for climate change studies, heatwave analysis, and vegetation productivity research. And this is all for today. Thanks for watching. If you found this helpful, feel free to like and subscribe, and let me know if you want a follow-up on how to analyze these LST outputs. Although I plan to upload another video where I show you the post-processing of these datasets, which will be prepared for further analysis.